Welcome back to another video. Like I said in the previous one, that we will be now coming up with a method which allows us to perform edge triggering. What I mean by that is instead of making our circuits to react to the entire positive level of the clock, we will be trying to make them react to their positive edge, right? So that the ambiguity is eliminated. Fine. There are many ways we can use integrators and other circuits, but the one that is in your course and which we often use in designing flip-flops is known as edge triggering using the master-slave configuration. Now, in this configuration, as you can see on the schematic here, I have used two latches. Fine. The first one that I'm showing here in the red one, it is what's known as a master latch. And this master latch feeds another latch, and then that latch becomes a slave latch. Right? They're connected in series, which means the output of the master latch acts as an input to the slave latch. And overall, you have the input, external input D, which is the input to the first latch, which I am showing by D subscript M. M stands for master. Then QM is the output for the master latch, which drives the input of the slave latch. And QS is there. I'm showing both the outputs QS and Q bar S. And we are actually interested in finding a relationship between this output Q, which is QS, and the input D, which is the input to the master latch. An important difference in the two circuits is that they are being fed by the same clock, but the master latch gets an inverted clock, shown by this NOT gate, and the slave latch gets a direct clock. Right? And I have written here that the first latch, the first D latch known as the master latch, is enabled when clock is 0 because of this NOT gate. Because when clock is 0, this clock NOT gate will make it 1, and for that period, your master latch will behave because latches respond to positive edges, positive levels, sorry, positive level. Similarly, the second D latch is known as a slave latch, and it will be enabled when clock is 1. Now, to understand the behavior of this circuit, we will draw a timing diagram here. So I've already drawn some waveforms. Here is my main clock. It has a low pulse, then a high pulse, a low pulse, and so on. There's a periodic signal. Then I have this external input D, which is the input to the master's latch DM, and it goes low, then it goes high, then it remains low throughout. Right? Then I have to look for two clocks, the master clock CM and the slave clock CS. The slave clock will be the same as main clock, but master clock will be the inverted version of this main clock as slave clock. So if this is 0 here, it will be 1. This is 1, 0, 0, 1 because of the NOT gate. Fine. Now let's first of all plot what will be the output Q of M. And so let's start plotting Q of N, which by the way will be the input to the slave latch. Now this is a latch, this is a typical latch behavior. So it will wait because this, remember that this master, it actually reacts to the inverted clock. So it will be reacting to this CM. Fine. So maybe I will draw a projection so that you are better able to visualize it. This is the transition for my data, external data. Fine. And let's use this one. All right. So up to this point, your D input is 0, so it will follow suit, although this is a positive edge. Now, please remember this is a positive level. So the input goes high at this point, so it will follow. Then there is a negative clock, so it will remain constant for this negative clock. Fine. then pause to clock for this particular master latch. उस टाइम पे आपका डेटा 0 है, so it will drop down to 0. Fine. So let me draw. I think I should use a different color so that it is visible in a better way. Let's use this one. Fine. So up to this instant 0, then it goes high, remains high up to this instant. Fine. Now this output of the master latch, it acts as an input to the slave latch, and the slave latch responds to the direct clock. And this is important here. Master latch to the inverted clock, that is CM, and the slave latch to the direct clock. Now let's plot the output of this is the one we are basically interested in, the output of the slave latch. So we are now plotting QS, which by the way is my external output, Q. Please remember it will react to this main clock which I am showing in red. So we'll have to, this will act, the pink one, it will act as a data input for this latch, and the red one is actually the clock. So if you plot it up to this instant, the clock is 0, so nothing happening. Then after this, it will track what is happening at the pink output. So it will follow pink output like this. Fine. And then it will drop to 0. So these are my what you call waveforms. Now I have to see what is the relationship between my external input, which is my D, and my external output, which is my Q. And this relationship is established with respect to the external clock CLK. So the waveforms I'm interested is, of course, this main clock, this external input, and this external output. Fine. So let's analyze what's happening. My clock goes high here, and at this instant, the external input D is high. So output is low. At this instant, it goes high. Fine. But during this positive level of the clock, it also drops down 0 here. But as you can see, it continues to stay at 1 throughout. So it's not level triggering. I have actually achieved edge triggering, wherein my flip-flop now responds only to this positive edge the instant it goes from 0 to 1, because otherwise it should have dropped down 0 here also, but it's not happening. It's keeping a constant value of a flat value of the data input D. So this is how we achieve edge triggering using a master slave configuration. And the drawback here is that I need actually two latches to come with a single flip-flop. But this is the one widely method used here, right? So this is how we achieve triggering. But you should always remember, like I said in the previous video also, that a latch, it is implied, it is always level sensitive. So we don't use a full term level sensitive latch. We simply use latch, and it is implied that since this is a latch, this is going to be level sensitive. Fine. So saying level sensitive latch is redundant because whenever I say latch, by definition, it is level sensitive. Similarly, saying edge triggered flip flop is redundant because every time I say flip flop, it is implied that it will be edge triggered. And how do we achieve edge triggering? There are multiple methods. This is one of the methods wherein we achieve edge triggering using the master slave configuration. Fine. And if you can closely look at these waveforms, you can see that the relationship between the external data and the external input data and external output data, it actually transitions, it actually triggers only at the positive edges rather than the positive levels. Fine. So we'll be discussing a few flip-flops. You see, from a functional perspective, As far as storage is concerned, both will store 1 bit, latch as well as flip-flop. The only way they differ is the way they trigger, the way they behave to the external clock signal. Right? That's where the difference lies. So if I have a D latch, then on the counterpart, I also have a D flip-flop. Both will store 1 bit, both can store both zeros and ones, but the way they will react to the clock, that will differ. Similarly, if I have an SR latch, I can have a SR flip-flop. Both will store one, both will have the same problems which is there in the SR latch. Only difference is the way they react to the clock. Right? So immediately after this, we'll be taking another storage element that goes by the name JK, and we can have JK latch, and we can also have JK flip-flop. Only difference is if it is a JK latch, it will respond to the level of the clock, and if it is a JK flip-flop, it will respond to the edge of the clock. Right? So we'll end this video here.